Alright, welcome back to the set slide. Unfortunately, these slides in this chapter is really just a lot of definitions because sets are really how we're formalizing mathematics, and so there's a lot of things that we've already formalized, right? And so we have to learn the language. But there should be a few more examples in this half of the slides that we're going to finish today. Okay? So let's go back. We last learned about unions and intersections, which made a lot of sense, right? Combining elements or taking what's in common, just normal Venn diagram operations. Let's go further. Let's talk about unions of a bunch of sets, or intersections of a bunch of sets at once, okay? So instead of writing this, which would be one valid way to write the union of a bunch of sets, A1 through AN, we have a fancier notation for that as well, okay? So instead of saying this, we can say a big fat union starting with an index, like we're doing a for loop even. So I starting at 1 going all the way to n, then please do a of I, okay? And union them all together. That's how you read it. And that's equivalent to, all right, I starts at 1, take a of 1, union it with a of 2, because I gets a chance being every number between 1 and n. You see that? Union them all together, you get the big, large intersection of a sequence, union of a sequence of things. And then you can do the same, flip this around to make it an intersection, okay? And this really is like a mathematical for loop. You start your counter I at 1, you increase it until it's n, and you just keep on unioning, okay? So for intersections, if you want to intersect all the ai's from 1 to n, you write it like this. Start I at 1, go up to n, and then intersect all the ai's, okay? Does that make sense? Let me give you an example to help this make sense. So let's let a of I be defined to be this. It's I and 2 times I. So every number and its double. Isn't that nice? So the I is like a little variable that helps you build this set even. So a of 7, for example, is the number itself, so I and then 2i, so 7 and 14. Isn't that cute? So see if you can do, okay, what's this? What is this big union from I equals 1 to 3 of all the ai's? Okay? Did you give that a try? So that's equal to a of, I starts at 1, right? A of 1 unioned, this is just a bunch of unions, a of 1 unioned a of 2, unioned with a of 3, okay? Which is equal to, now we can do it, okay, 1 and its double, right? I and 2 of I, 1 and 2 times 1, that is 1 comma 2, right? Union, what's a of 2? That's 2 and 2i, 2 and 2 times 2, so 2 and 4. What's a of 3? That's 3 and 6, yeah? Oops, I meant to write a union, not a comma. There we go. And if we union them all together, we get 1, 2, 3, 4, and 6, right? Looks like it. And so that's the big union of a sequence of sets. See how that might be useful? Instead of saying all this and this, it's a bit more compact when we say it like that. And sometimes that makes more sense. Okay? That's not too bad. I've talked about how to like add stuff to a set, but I haven't talked about how to remove stuff from a set, so let's talk about that too. That's called the set difference, right? You have like a minus, where union was like our plus, right? So here is a form of set subtraction. A minus b is defined as all the things in A that are not in B. So start with everything in A, and then take out the stuff that are in B, okay? All the stuff in A, but not in B. That's how it's translated to logic. So if this is A, 1, 2, 3, and B is 2, 3, 4, what is A minus B? It is, okay, start with all the things in A. Just draw A. 1, 2, 3. And then, I guess we can draw B as well. Here's B, 2, 3, 4. And then you take out all the stuff that was in B. So start with A, take out all the stuff that was in B. And so you're left with just this little slice here. Whee! Just 1. You see that? This is A minus B. And it's okay if B holds stuff that isn't also in A. Based on the definition, that's not a big deal. Okay? So this is just the set containing 1. All right. And then we're finally ready to go back to that universal set idea, because that gives us something called the complement. You might want to negate a set, okay? The way to do that is to use a complement. So take a set A and make the complement of A, which is everything that's not in A, for example, okay? And to say that, to say like, all right, I'm starting with 1, 2, 3. I want everything that's not 1, 2, 3. You have to implicitly have a concept of a universe, right? You have to know what everything else is that you're talking about. So you have to have that universal set, okay? So the complement of A is everything in the universe that's not in A, okay? So you can also define it like this using subtraction. It's U minus A. It's all the stuff in U that's not in A. And this will make the most sense with an example, okay? So here, let's let A be the set of all the positive integers greater than 10. So here's A. A is 11, 12, 13. And let's say that the universe is all the positive integers. You see how that was like what we started with, and we were kind of filtering some out? So like our universe is z plus, all the positive numbers. So remember that is just this, right? All the positive numbers, not 0. 1, 2, 3, on and on and on forever. So if that's our universe, what is the complement of A? It's everything in the universe that is not in A. So it's everything in the universe taken out. Take out all the stuff in A, though. Okay? So what is that? What is A bar, A complement? That is, well, it's everything in the universe, all this, except for these things. Infinitely many things. So, what's left? 1, 2, all the way to 10. See that? That is the complement. It is all the stuff not in A, right? But in order to say not, you had to have a concept of where you're coming from, like what is everything else, right? Where are you thinking? So that is the complement. I hope it sheds more light on this idea of the universal set. Okay? So that's the set difference, or subtraction, and complement. Kind of like negation, because negation appears secretly. Okay? So now that we have all these operations under our belt, we can talk about how to transform some sets into other sets, and talk about equivalences, right? Equalities on sets. And the reason we get all this for free is because of logic. We've defined all this stuff using logic. And so identities on sets, ways that we can make the same set or simplify a set, they're going to look a lot like our logical identities, which is quite nice. Okay, so I got a big list on the next slide. Let's look at those. And then we'll prove this law, which is exactly Demorgan's law, but just for sets. Okay, weirdly enough. So if you squint, this is just logic all over again, isn't it? So this is union is like or, intersect is like and, empty set is like false, universal set is like true. Okay? Think of it that way, and it really makes sense. It's going to work out. So like associative laws for union and intersection, commutative laws. It doesn't matter which one you which one you intersect, which one you union first. It's all fine. You can distribute or over intersection, union over intersection, and intersection over union. Not a big deal. Anything union with the empty set is just that thing, right? Does that make sense? Anything intersected with the empty set is the empty set, because they have nothing in common, right? The empty set. That's all you get. And then the universal set is just everything, right? And once you union with it, you're stuck with everything, right? And if you intersect with the universal set, you just get that original set back, because obviously A is contained in this, right? It's smaller than it. Okay? Double negation, equivalent, all this stuff. You have Demorgans. If you want to take the complement of a union, that is the intersection of the complements. See that? Same for this. So, yeah. Complement really is like negation for sets in a very precise way. So let's prove some of these identities. Let's at least prove this one. Let's prove the first Demorgan law. So if I take the union first and then the complement after, see the ordering implicitly there, that's the same as first taking the individual complements and then intersecting. Okay, so let's do that. And let us prove it like this. Okay, let's prove that everything in this is also in this. Remember how I told you how to prove equalities? Boop, up here. Let's prove that they're all contained just like that with a bunch of biconditionals. All right, so let's start with, we've got an x, right? We want to prove that every x in this is also, way down here, in this. Okay, that's where we're going. So that's the end of the line right there. That's where we want to stop. So let's get there. Let's expand all of this. Okay? Dun, dun, dun. So x is in the complement of A union B. What's the complement defined to be? Well, it's everything that is not in the original set. So let's do that. A is in the complement of A union B if and only if it's not true that x is in the union of A and B. So I just got rid of that little complement symbol by introducing a not logically. Isn't that nice? So you might think you want to like push that negation inwards and do something like make x in A the negation become, and it really is x not in A, but we can't really prove anything about not in, so that's kind of useless to us. What we can do, though, is unravel the definition of union. You remember what that is? It's up here. So something is in the union if it's in one or the other. X is in A or X is in B if it's in A union B. So that is what we can use to get us farther. Okay, so let's unravel the union bit. So this is saying it's not true that X is in A or X is in B. And then, oh man, can we actually do something with that negation? We can use Demorgan's in logic, normal logical Demorgan's law, okay, to push that negation inwards, and it becomes not x in A and, right, because that gets flipped from an or to an and, not x in B. Still, I'm going to hold off on translating from that to that. You'll see where I'm going with this later. Because this definition, right, x is not in A, I guess I could technically use it. It is the complement all over again. Okay? Do you see that? That is the trick. So I guess I could go farther. I could use the not in, but this is enough to notice that I can replace these with the complement of A and the complement of B. Isn't that nice? So if and only if, this just means x is in A complement. And this one means that x is in B complement. Oh man, we're almost somewhere, because now we can get rid of this and by replacing it with a intersection. Remember the definition of intersection, right? That is, something's in the intersection of A and B if and only if x is in A and x is in B at the same time. They're shared, right? So that is if and only if x is in A intersect, or A complement intersect B complement. And what do you know? We started here. Everything in here is also in here, which means the sets are equal. Okay, that's what we wanted to show. So therefore, A union B complement is equal to A complement intersect B complement. It's like the Demorgan's law for these sets, okay, instead of logic. So that is a fun proof using identities. And now I want to give you an exercise that involves you using just the table to rewrite things using the identities. Okay, so let's go there. So now I want you to try to use the table, use the identities to prove this. Okay, prove that A intersected with B itself intersected with B complement. Prove that that's equal to the empty set. Okay, and use each identity as you use it. So this is like, the empty set's like false, remember? And this is like, that's a special rule with something and its negation, right? Remember that from logic? That's going to always give us false, right? So think of it this way. False is defined to be the empty set, essentially, and true is defined to be the universal set. That'll help you unravel these definitions and understand them. So we start here, and let's start on the left, and then whittle our way down to the empty set. Okay. So we have A intersect, B intersect, B complement. So we got that, and then that's where we start, and then let's get rid of this, right? Anything intersected with its complement is the empty set. That's a complement law. That's the same as A intersect empty set. Complement law. And then this automatically becomes the empty set because anything intersected with nothing is nothing. That's a domination law. Okay? Did you get that? So very similar. Really, it is equivalent, logically equivalent deep down to our logical identities. Okay? These set identities. It's a long word. All right. Now that we have those, let's build up some more math. Because we like to, I don't know, we like to graph things, right? We like to have pairs of values with a certain order. That's important. Let's make the set of all possible ordered pairs, right? We have those. That's very necessary. So the set of all ordered pairs is called a Cartesian product, named after Descartes, of course. And so remember that the whole idea of set theory is that we wanted to define every single thing in math in terms of sets. So if we have an ordered pair, we have to make a set out of that somehow. And so the silly definition that works is let's define the ordered pair AB, A first, then B second. Let's define that to be the set containing A and the set containing AB. And that's how you know which one came first. The one in the smaller set is the one that comes first. Crazy. You don't have to worry too much about that, but that's how ordered pairs are defined, because why not? The reason you can't just define an ordered pair to be the set A comma B is because that's equal to B comma A, right? The ordering is lost. So this retains that ordering. That's why we have to define it in a fancy way. But now we can talk about Cartesian products. So the Cartesian product of two existing sets, is the set of all ordered pairs, where the order is important, right? The first element is taken out of A, and the second element is taken out of B, okay? Let me write it as A cross B, okay? So if A is 1, 2, and B is A, B, C, what is A cross B? It's the set of all the ordered pairs where the first thing's in A and the second thing's in B. We got, well, we can take the first thing of each, with the 1 and the A, make an ordered pair out of them. We can keep the 1 and take the B instead. That's another ordered pair. 1C, 2A, 2B, see that? 2C. These are all the ordered pairs in A cross B. Does that make sense? It's a set of all the possible ordered pairs where this comes first and this comes second. Ordering is, of course, important in an ordered pair. 1A is not equal to A comma 1, right? It's not sets. Or it's a special kind of set, depending on how you want to think about it. So that's a Cartesian product, and A cross B is a set of all possible ordered pairs between those two sets. All right. And of course, you can do that multiple times. You can have ordered triples, right? Those look like A, B, C, right? And those are Cartesian products of three things. Not an issue, right? The first thing comes from A, the second thing comes from B, the third thing comes from C. And then you can generalize this to Cartesian producting together multiple sets, more than just three, as many as you want. So those are called n-tuples, okay? Those are elements of Cartesian products for greater than two sets, okay? So here's a 4-tuple, we say. It's got 4 things in it. It's an element of this cross this, cross this, cross this, because you can take the 2, you can take the A, you can take the B, and you can take the 7. Isn't that nice? And so that's an element of, or an ordered quadruple, or a 4, you can write that as like a 4-tuple. Well, it's weird notation. Before we go any further, I want to talk about the pronunciation of this word, because there's, just like do the natural numbers start at 0, this also gets mathematicians angry. So the reason I'm pronouncing it as tuple is because that's how I learned it, and it just seems normal to me that way. That's how I've heard all of my professors say it. So tuple is pronounced, you have options actually, pronounced as either tuple, like I'm saying it, or tuple. Okay? Like when you're saying quintuple or something. That's how you pronounce it. That's your other option. I say tuple, okay? You can say tuple if you want. And then if you have really long ordered pairs like this, 2A, B, 7, that's actually how strings are born, guys. You can use string notation instead of Cartesian product ordered pair notation. You can just say 2A, B, 7 instead of 2, A, B, 7. Interesting. Now you know how strings are born. A string is just an ordered pair of a bunch of characters. So it's taken out of the set that contains every English character, for example. That's a string, all the ASCII characters. Isn't that nice? Okay, so let's have some examples for us, and I want you to try these. Okay, so let's start with this one. Let A be the set just containing A, B be the set containing B and C, and then C being the set A, B, D. So I want you to write all the possible ordered pairs, union of A and B, union with all the possible ordered pairs of A and C, right? Once using the normal n-tuple notation with the parentheses and the commas, and then again using string notation so that you know both. And then you can totally cross one with itself, cross a set, take the Cartesian product of a set with itself, see if you can figure out what B squared should be, right? B cross B. So think about those, and then we'll come back and do them together. Okay, so maybe we can do these separately. Let's do A cross B and A cross C separately, and then we can bring them together at the end. So what is A cross B? It's all the pairs of something in A and then something in B. So it's either AB or AC, right? That's it. AB and AC. So that's A cross B, and then A cross C is equal to, well, anything from A, try everything, and then everything from C. So it's AA, AB, and AD. The set of those three ordered pairs. And then AD. And so their union now is just all this stuff that they have. So we got, I'll try and do it in alphabetical order as much as I can. AA first then, right? AA, we have AB, do we have AC? Yep. AC, and we also have AD. So that's everything they all have together. So it's 4 distinct elements, yeah? So that's normal n-tuple notation. And then you can also write the set, that is this union, of these two things using string notation, because every ordered pair can just be written as a string instead. Just put everything next to each other instead of parentheses and commas all over the place. So that's AA, AB, AC, AD. And this will come up later in the class when we talk about strings. So that's that. And then let's do B squared, because that is just B cross B, right? B Cartesian product B. It's all the ordered pairs where one element, the left element's in B, and so is the right element. What's that? Well, it could be BB, right? B could be first, then the next thing could be B, could be BC, or you could pick C first. CB, CC. Does that make sense? And again, you could write that as a bunch of strings if you'd like. Not a big deal. Another thing that has to do with the size of these, it's not 2 to the power of anything like power sets are, but when you're talking about the size of a Cartesian product, look what happens. It happens to be the product of their sizes. Okay, because it's like you got one thing from here, one thing from here. What are all the different possibilities, right? It just multiplies. It's like a for loop, a nested for loop. So that's that one. And now I have another one for you to try. Okay, this one involves proving this time. So go ahead and take these definitions and use logic and them to prove that this is equal to this. So you're going to follow that same pattern that I was doing before. Where was that? There it is. So it's like some random element is in the original one, if and only if it's in the one you're trying to prove that you can get to. So just with a bunch of chains of biconditionals, that's where I want you to go, okay, using these laws. So here's the definition of a Cartesian product. X and y is in A cross B if the x was in A and the y is in B, right? And then x is in the intersection if this is true, like we know. X is in the union if this is true, like we know from before, okay? So we're going to prove that Cartesian product distributes over, that's not union, that's intersection, right? There we go. So that's what I want you to try. So see if you can do it. Let me start you off. We have a Cartesian product, so it's not just x is in something. It's we have some pair in A cross B intersect C. Oops. And then you need to go using logic all the way down to here, where that same x, we found that one of the sides is in one of these and another is in the other. Okay, so it's still going to involve x and y, but it's going to be a bit more fancy. Okay? So think about it like that, and then we'll get there. So x comma y is in this whole big thing. All right. So assuming you've given that a try, let's take a look and see how I might do it. Let's see. I guess the outermost operation here is the Cartesian product, so let's split this. Let's split this up into this side. So this means x was in A and y was in B intersect C. Intersect C. That seems to work. Okay, then we can also get rid of the intersection, bring it back to just plain old logic. So we got x in A and y in B, and y is in C, right? I'm getting rid of the parentheses that would normally be here, but it's associative. A bunch of ands, not a big deal. So I have x is in A and y is in B and y is in C. Okay? Now, I need to somehow break it up this way. Right? Somehow need to break it up this way, which is going to involve x in A and x in B and x in A, or sorry, and y in B, and x in A and y in C. I'm going to need those all over again, which kind of looks like this, right? X is in A and y is in B and x is still in A and y is in C. Something like this. That's what I need. Does this follow? It does, actually, because I can just use some associative laws to draw some parentheses, and it's totally fine for me to duplicate x and A. I already know that it's true. I can write it twice. Not a big deal. So I'm moving things around, drawing parentheses. This leads to this, okay? And that's the form that's going to get me some Cartesian products with the A's and B's and A's and C's. You see that? Now I have two separate Cartesian products. I know that x, y is in from this one, going backwards, right? From that to that. X comma y is in A cross B. And, right, from this one now, and the and. X comma y is in A cross C, because there's an A and a C in this one. And now I'm home free because the last thing I have is this and I can go from this side to this side to make the intersection. See that? So x comma y must have been then in A cross B intersect A cross C. Isn't that lovely? And that's what I wanted to show. So therefore, A cross B intersect C is equal to A cross B, in parentheses first, intersect A cross C. And implicitly, we kind of did a for-all proof, right? We made x and y arbitrary, and that allowed us to conclude, like, okay, yeah, everything in this one is also in this one, therefore they were equal. Okay? Definitely yell at me if that's not making sense, but that's how we're proving some of these laws, some of these identities of set theory. Okay? All right, so I just led us up a little bit to strings, string notation. Let's talk about those in general, because they really are just Cartesian products. It's very weird, but it works. Okay, so any n tuple of characters, where a character is just something from a set, right, is a string. Interesting, interesting, interesting. So maybe we have a string s, and that is an length n string, so it's in a to the power of n, right? It's just n characters taken from a, where a is called the alphabet. And that's just, doesn't have to be like our normal alphabet, it could be anything. It's just the set of characters that you use to build your string. You can use. Okay? So for example, if my alphabet is all the lowercase characters, then the string hi mom, without any spaces, is in a to the 5, right? Because it's a string of length 5. Isn't that nice? And, okay, because of this, strings are secretly n tuples, but n tuples were secretly defined using sets. Well, that means a string is really just a set. And I unraveled the definition for us, and it ends up to be that. Not that we have to care. But this is set theory. This is the reason it got that it was invented, so that everything could build on top of itself like this. And we can define all of mathematics, all of the stuff that we even care about in computer science, like strings, using sets. Isn't that nice? Let's do some more string stuff now. So we can have binary strings. Those are common because that's the simplest possible alphabet with multiple characters. So that's a binary string is just a string made up of the alphabet 0 and 1, right? So like 1 0 1 0 1 0, that's in that alphabet 0 1 to the 6th, right? Because it's got 6 characters in it, and this is a binary string. Not too bad, right? You can also have the empty string, okay? And we call that lambda. Lambda is the unique empty string, because there's only one kind, right? Just like there's only one empty set. It's the only string whose length is 0. And lambda is the Greek L, and so I think that the lambda comes from the German leer, which means empty or blank. Okay? It's interesting that they have that word too, just like Spanish. It means something completely different. So that's the empty string. And then we can talk about the concatenation of strings. Okay, this is just like the plus operator in C++. So for example, you can concatenate s and t. If s is this and t is that, that just becomes, well, st, where you got s and then you got t right next to each other. There was s, there was t. You just plop them next to each other. That's how you concatenate things. It's just like the plus operator in C++, on strings at least. And then lambda, the empty string, when you concatenate with lambda, it just kind of goes away because it's nothing, right? It's like you're adding the empty string. So s lambda s is the same as s lambda is the same as s. Okay? You can cancel away the empty string because you're just adding nothing to the original string. Okay? And so it really is just C++, essentially ABC plus DEF, right? It gives you back ABC, DEF, and then like, I don't know, ABC plus the empty string. That's still ABC. Right. Well, that's just stuff you already know. Just new symbols for it is all. Okay. So lambda really does just go away. It's like if I have hi mom, hi lambda, m lambda o, lambda lambda m, that's really just hi mom. Because these empty strings, when we concatenate them, they just go away. Okay. That's the idea there. Okay. Moving on to partitions of a set. This is another logical thing that we understand in English, but we would like to define formally in mathematics. Let's talk about splitting up sets into different pieces, okay? First, we need to talk about disjointness, though. So if you have two sets, A and B, for example, we call them disjoint if they don't share any elements, so their intersection is empty. We say that they are disjoint. So maybe A can be 1, 2, 3, and B can be 4, 5, 6. They are disjoint, A and B are disjoint because their intersection is empty. They share nothing. Okay? Then you can have a bunch of sets, A1 through AN, a ton of them. We call those sets pairwise disjoint if every possible pair of them, like this one and this one, or this one and this one, every possible pair is itself disjoint. Okay? You can define that in math to say like every index I and j where they're not equal, they're disjoint. See that? It's called pairwise disjoint, which is nice to have. That means none of them share any elements with each other. Okay? They're all separate. That lets us define what a partition is. When you have a set and you partition it, you make a bunch of non-empty subsets. That's one key thing. You make a bunch of non-empty subsets of S, okay, such that each element of S is in exactly one of those subsets. Okay, so that's like all that really is. We're going to get into fancy math, but all it is just separating elements of a set, okay, and just sectioning it off. Okay, into non-empty subsets that don't overlap. That's all a partition is. Okay, let's talk about that in fancy math, but I think you understand what it really means, right? So here is a partition. Here's my A1, here's my A2, here's my A3. When something's a partition, this is like the set C, let's say. This is a partition. These three subsets are a partition of the set C because of this, right? Because they all are subsets of the original set, right? I didn't add anything extra, like that was out here. These are all subsets of the original set C. So that's the first check. Then they're all non-empty, because it would make no sense to have an empty partition, right? An empty set, you could just get rid of it, right? So check, those are all have at least one element. Then they're all pairwise disjoint, because they don't share anything. Like there's nothing left over, right? These don't share anything, and these don't share anything. They're all disjoint. They separate the set, okay? They partition it. And then each of those individual pieces, each partition, each little subset, together, they make the original set, okay? So we're not leaving anything out. Everybody's included in at least one, or sorry, exactly one of these subsets. Does that make sense? So here is me coming up with a 3-set partition of this set C. Okay? I did it already. So it looks like the koala and the squirrel are together, the raccoon and the cat are together, and then the dog is all by himself. Okay? Whee. And so I can make, I guess I call it C1. That would make more sense. Or it doesn't matter. We can keep it A1. I was saying S and A's over here anyway. A1 was koala and squirrel. And then A2 was raccoon and cat. And then A3 was just the set with dog in it. Okay, and so all of these satisfy the requirements to be a partition of the original set C. Okay? So with that, we are almost ready. All right, almost finished with these slides. So let me check the time just briefly, make sure we're on track. I want to give you an example that actually involves math. Okay, so here are some sets, A, B, and C, and D as well. And I'm defining them like this. So A is all of these numbers, B is all of these numbers. These are real numbers, right? Rational plus irrational. These are all the real numbers that are strictly less than -2, right? All the real numbers that are strictly greater than 2. All the real numbers whose absolute value is less than 2. Whose absolute value is less than or equal to 2. See how I'm reading that? So I want you to think about these. Do A, B, and C form a partition of R? Do they satisfy each of these requirements? And do A, B, and D form a partition of R? Okay? So try each of those, please. So, do these three form a partition of R? All right, so we got to think about that. Let's draw a number line. Here's 0, Here's -2. Here's 2. So A is everybody, every element that is less than -2, but not including. Okay, so this is A over here. Okay, and B, if we union that, B is everybody greater than 2, so not including 2. Whee, that's B. And then C is every value whose absolute value is less than 2, right? So still not including those 2, but all of these, that's C, okay? So does that help you determine whether or not these are a partition? So they're all subsets of the real numbers. They're all non-empty. They're all pairwise disjoint. They don't share any information. But this one isn't true, is it? They don't make the original set. They don't partition all of the real numbers because they missed out on -2 and 2. You see that? No. So the answer is no. A union B union C misses. It misses the set -2 and 2. Those are not included, and they should be included to form a partition of R. Okay? And so D saves the day, doesn't it? Everything else is true, and D does this. D takes those individual elements, -2 and 2. And so this one does form a partition of R. That one's no, this one's yes. And the reason why is all these, right? They're all working out, right? So they're all subsets of R. They union together. They're all pairwise disjoint. They don't share anything. Don't share any elements. They union together to be R. A union B union D. That is in fact R. And then the final one, they're all non-empty, right? We need each of those for it to be a partition of the real numbers. Okay? Isn't that nice? So that's that. And now let's do one last thing. I want to talk to you about sets in programming, okay? Because we have those, right? You've used this. In C++, you have the set data type in the standard template library. Set is a balanced binary search tree, isn't it? But it has the normal set operations. You can insert things, you can union together sets. It all works out. Because it's balanced, it's log of n to look up, insert, delete, things like that. You also have the unordered set data type. That is a hash table, and so you have very fast lookups. Okay, so I encourage you to look at the documentation for these two types in C++ and learn a bit more about them, but they exist. One thing that's really nice to do, instead of making a fancy data type, is to formalize some piece of math or some programming concept in a programming language, but it doesn't have to be efficient, okay? A formalization does not have to be efficient. It just tells us more about the subject, okay? It helps us explore. It doesn't have to be cool, okay? A formalization is an easy-to-understand reference implementation. Emphasis on the reference. It doesn't have to be fast, okay? And so what we can do is let's model sets and unions and intersections. Let's do it in Racket. I'll need some helper functions, and I'll show those to you. But let's make sets. Given what we know about them, we've learned a lot of things, let's model those in Racket. Let's see what it means to be a set. And so here's my code that I've made for us. In Racket, let's model sets as lists. So like the set 1, 2, 3, oops, can be the list 1, 2, 3. Isn't that nice? But lists in Racket can have duplicate elements, so it's not yet a set. So let's remove the duplicates of every element in a list, and that will make it a set. See? So I can have this make set function that takes a list and just removes all the duplicates, and then it becomes my formalization of a set. Does that make sense? So this is how you remove duplicates. It's a recursive process. So if the list is empty, there's nothing to remove duplicates from, you're good. Otherwise, if the list is non-empty, split it into the first and the rest of the list, first element and the rest of the list. Then you need to get rid of all the duplicates, because maybe first appears a bunch of times inside of the rest of the list. So what we'll do is we will remove all the extra occurrences of first in rest using filter. Get only the things that are not equal to first, please, from rest. And that's the filtered rest. Then we can recursively remove any other duplicates from that filtered rest, from that smaller list with all these duplicates gone. Okay? And then finally, you can build up the original filtered list that has no duplicates anymore. Okay? So definitely try this out. It's really cool, and it works. So we can make a set and remove the duplicates from that set. So for example, here I am running it. I can make the set A and B from these lists, L and L2. Let me print those. Or let's do print F. A is this, and B is this. Oops, I forgot a new line. I'm so used to it doing automatically for me. So here's A and B. They've had their duplicates removed. They've been built from these lists, though. Okay, so 1, 2, 3, and 2, 3, 4. Cool. And then you can do list stuff to define element of, right? That'll return true if X is an element of S. It's really nice in Racket. You can have random characters as function names. Totally fine. Racket doesn't care. So I can define this operator. It's just a function. So yeah, we can use the member function on a list. If X is an element of the list S, because that's how I'm formalizing my lists, then return true, otherwise return false. It's weird that member itself doesn't return true or false. It's just a weird historical reason that it doesn't, but you can coerce it into true or false. And so that's very easy to check for membership. Just use list member, which checks if something is in a list. And so, yeah, one's in A, but one's not in B, for example. And then union is not too bad. You can easily union some stuff by appending lists, right? By going to Racket, here's the list 1, 2, 3, appended to the list 4, 5, 6. That just adds them to each other. Kind of like string concatenation. That's appending. And so if you want to union two sets, just append them to each other because we're modeling them as lists and remove their duplicates. Okay? So the union of A and B is 1, 2, 3, 4. Makes sense. And then finally, their intersection is a bit fancier. You have to do some filtering and things like that. So I have a little helper function a helper variable. Every element in S1 and S2, that is their union. And then we have to go through each of those elements from both of these and make sure that it's in both. Okay, so we find all the elements that are in both of those lists. So filter, based on whether or not it's using our definition of inside membership. So it better be true that X is in the first set and X is in the second set. Bam. In that case, it was in both. Build up that list, please. And then also remove any duplicates, just in case. Okay? So that is intersection, and it'll get and pick out all the things that are in common. And this is a formalization. It's much faster to do it with a hash table or binary search tree, but we didn't. We just used lists. But we were able to model what it means to be a set, and it's a bit easier to think about, okay, and reason about. So it's nice to formalize things, and then once you really understand them, make them fast. Okay? That was the point of all of that. And so for my final trick, we made it to the end of these slides. The last thing that I want to do is talk to you about your next midterm, okay? Your first midterm. You have a test coming up soon in 2 weeks, and so let me create the page for that right now, and then I'll restart this video and tell you all about it. All right, I'm ready with the midterm details. So week 6 is when it's going to be, and I've made this nice module on Canvas all about it. So I'll release these 2 pages right now, midterm 1 info and extra credit assignment. So let's look at both of those pages. The first, midterm 1 info. Let's talk about when the midterm's going to be. So it's going to be week 6. I'll make it available at 2:30 p.m. on the Tuesday, and it will be available until 5:30 p.m. on the Thursday. Normally, I like to make my tests out between Thursdays and Fridays so that you can hit 2 of my office hours, but sadly week 6, the Friday is a holiday, so I will just make the test be available between Tuesday and Thursday instead, so that you still have a chance at 2 of my office hours if you want to take the test during them. Okay, so that's that. You can start whenever you want within this time frame, but once you click start, you get an hour and a half to complete it. A timer starts counting down when you click start, and that should be plenty of time. Okay. The topics on the test will be the following: the first 2 chapters of your Xi book, the first 2 homeworks that were about those chapters, and then all the lectures through week 5, but anything after those chapters is just kind of extra and will be appearing on a future test. But I might review a little bit, like all the chapters build on top of each other. I might review a little bit of those concepts, so that's why I say through week 5. Okay, so those are the topics, and one nice thing about this particular exam is it's a lot of, like, it would be a lot of proving. It's very hard to ask you to prove things on a test that's online, and so I'm just going to make this first midterm multiple choice, so you're welcome. Future ones will not be entirely multiple choice, but you might see a few multiple choice questions, but this one will be entirely multiple choice. Okay. Also, as this will be true of all the tests in my class, I don't want you to memorize anything. You can look up whatever you want. The test is open book and open notes. The one thing you can't do, because of course it's a test, is talk to another human, someone other than me. If you'd like, you can take the test during my office hours and ask me questions while you take it about the questions. That's the one thing you're allowed to do. I'm the one human you can talk to while you take the test, right? That seems fair, I hope. And if you'd like to review or study, one nice thing that I have made available for you is the test from the last semester I taught the class. So here's their midterm one. You should expect to see very similar questions, so please take a look at that. So that is the midterm 1 info page, and then with every exam I usually like to release an extra credit assignment. So here is your midterm 1 extra credit assignment. What I would like you to do, if you feel like it, if you feel like getting up to 2.5% extra credit on top of your final grade, you can make a review video that goes over some topics that will appear or may appear right on the exam. So this is just for you. It's a discussion, so your peers will see you post these things and post your videos. So they will love you forever if you make a review video for them, okay? And it will give you extra credit, so why not? So you don't have to edit the video that you record, just post the raw video. You don't have to go crazy or anything. But I do have like a time, a length requirement for that raw video that you're recording with your review information inside of it. Okay, so here's the requirements. If you want to do the extra credit, you have to come up with a bunch of examples for concepts that might appear on the exam and go over them. Okay, feel free to get as creative as you would like. That helps you and your peers learn. The more exciting the examples are, right? You gotta explain what you're doing, demonstrate that you understand what you're talking about as you're going over these concepts. Maybe you just pretend like you're giving a short lecture, like pretend you're me. And yeah, that's really it. The rest is my time length requirement. So if you want 1.25% extra credit, then make a 10-minute video going over a couple examples. If you want the full 2.5% extra credit, then make a 20-minute video. Okay? Going over as many examples as you can fit. So that is that. Talk to me if you're confused about how to record yourself on your computer, or if you need any technology to help complete this extra credit, we can get you set up. But I do recommend this OBS program that I use to record these lectures. It's worked very well for me. You can also just use Zoom. You can start your own little private Zoom call and click record, and it should record your screen just fine and your voice. So one of those two options is probably the best one, but feel free to do whatever. And that is the extra credit assignment. So midterm, don't forget about it. It's going to be week 6, available between the Tuesday and the Thursday, and the extra credit assignment will be due midnight the day before the test is released, so Valentine's Day. Okay, so Monday at midnight is when the extra credit will be due at the latest. Okay, that is, I think, everything that I wanted to say. So please ask me questions if you have any about this stuff. And I am not releasing a new lab this week, so that is all that I have for us. You do get a new homework, though. Okay, so I'll see you next week.